So this will be a course given by myself and Vincenzo Mantova, University of Leeds. And it's about serial numbers and Transseries. It's essentially based on two papers that you can find in my web page with Vincenzo Mantova, or also on the page of Vincenzo. And there is also a survey that you can also find on my web page. I guess, I think Vincenzo has a different survey, so they integrate. And okay, so let me just start. So what are the serial numbers? Serial numbers have been invented by Conway in the 70s. Originally, they were invented to study combinatorial games like Go or chess. Indeed, serial numbers are included in a larger class of objects called games, which indeed include all these combinatorial games. Then gradually, a lot of more structure was introduced on the serial numbers, which was not present at the beginning, like an exponentiation, a derivation, and so on. And now, after all these developments, we see that serial numbers are intimately related to Transseries, and so it fits well with the program at Fields and with the course of Van den Dries on Transseries. So the serial numbers will be called NO for numbers. So it's a very big field, ordered field. It includes the real numbers, but it also includes the ordinal numbers. We will see exactly in which sense it includes both. And let me just make a quote. This is a quote from Conway. We obtain a theory at once simpler and more extensive than Dedekind theory of the real numbers, just by defining numbers as the strength of positions in certain games. So a number measures how good is the position for a certain player, but I'm not going to go into this aspect of games. It's just for the history of the subject. So it's intimately connected with games. So it turns out that not only includes the real numbers, but it has all the elementary properties of real numbers. So in particular, it's an ordered field, it's real closed, which means that every polynomial which changes sign as a root. So you can, and moreover, it includes the ordinal numbers. So for instance, the ordinal number omega, which is the first infinite ordinal number. So you can perform operations which are strange on the like omega minus 1 or 1 over omega, square root of omega. Then we will see also you can do logarithm of omega, omega square, omega to the square root of 2. So it's a strange object. Moreover, it also has a notion of infinite sum. You can also introduce infinite sums. So once you introduce infinite sums, you can speak about certain kind of analytic functions because they can be defined using infinite sums. And eventually, this notion of infinite sums brings us to the connection with Transseries, because Transseries are generalized series, which include Puiseux series and are very, very well, they are connected with the possibility of doing asymptotic expansions of certain functions at infinity, also for functions which are not analytic at infinity, but which can nevertheless be developed in the form of Transseries. Okay, so Transseries are also used in They are useful because they are in some sense a universal framework for solving certain kinds of differential equations of non-oscillating behavior. For instance, you can solve the equation everything related to the surreal numbers is as a non-oscillatory behavior. So for instance, you can define an exponential function, but not a sine and cosine function. You can only define sine and cosine on restricted intervals. Okay, so we shall discuss the connections between the surreals and Transseries, and also the connections with so-called Hardy fields. They are fields of real functions of non-oscillatory nature. Okay, so this is just a reminder on ordinal numbers. I assume that everybody knows ordinal numbers, but this is just, you know, what we need to do. 0 is an ordinal number. If alpha is an ordinal, alpha plus 1 is an ordinal, and is the smallest ordinal bigger than alpha. The sup of a set of ordinals is an ordinal. So for instance, you start with 0, then you have 1, 2, then up to omega, which is the sup of the previous ones. Then you have omega plus 1, omega plus 2. At some point you arrive at omega plus omega, which is called omega times 2, and so on, and so on. Of course, the class of ordinals is not a set, because if it were a set, you could do the sup and produce a new ordinal. So every set of the sup of a set exists, but not the sup of a class. So it's a proper class. Okay, I don't really need the way, so you can represent ordinal numbers inside set theory by identifying every ordinal with the set of its predecessors. For instance, 2 is just 0, 1, but this is not really needed. I mean, you need to know what ordinal numbers are. Now, surreal numbers, the surreal numbers, in some sense, are, let me just do an extra slide here. It's a binary version of the ordinals, surreals. So instead of having one successor function, you have two successor functions. Binary version of ordinals. The ordinals are called ON and the surreals NO. So you start with 0, you have a left successor and a right successor. And for some reasons, these are called -1 and 1. Then you have a left successor and a right successor. And this is called -2, this is called 2, this is called 1/2, this is called -1/2, and so on. So you keep going. So it's a kind of binary tree, but the height of this binary tree are all the ordinals. So this happens at level 0. On day 0, you have only 0. Then at day 1, you have these two new numbers. Then at day 2, at stage 2, you have 4 surreal numbers, and so on. You have 4 surreal numbers, and so on. So the picture is the following. You have essentially a surreal numbers is a binary, it's a function from an ordinal to a binary set, left and right, tells you whether to go left and right. So for instance, this surreal number here is right, left, so it's plus, minus. and this one is plus minus plus. So you have a function whose domain is an ordinal, because these operations can be done transfinitely many times. At some point, you have limit ordinals. You arrive at stage omega in which you have limit ordinals. So you get a function from an ordinal whose domain is an ordinal, and the domain is a binary set, which tells you whether to go left and right in this tree. The domain of the function is called the birthday. So for instance, the birthday of 0 is 0. The birthday of 1 and minus 1 is 1. The birthday of 1 over 2 is 2. So the length of the binary sequence is the birthday. You have two important binary relations on this big object. One is the tree-like binary relation, which is well-founded, and it's called simplicity. This one, X is simpler than Y. It just means that Y is a descendant of X in the tree. So for instance, this one is more complicated than this one. 2 is simpler than this. No? Simpler means closer to the root, in the path going to the root. 0 is the simplest element of all. This is the simplest. Okay. In terms, simplest just means that if you look at them as functions from ordinals to a binary set, simplest means that it's just the function, it's a restriction of the function. X is simpler than Y if as a function, X is a restriction of Y. Okay. You also have, instead, this is a tree-like ordering. You also have a linear ordering. The linear ordering essentially corresponds to projecting everything on an horizontal line. Sorry, this is not. Let me erase this for a moment. So imagine that you project the nodes of this tree on an horizontal line, and then you get a total ordering. So for instance, you have 0 here, and then on the left of it, you have this one that I called 1/2, then you have 1, then you have 2. So more formally, you can define this total ordering in the following way. So in a surreal number X has two, let's say, children, which are the immediate descendant, a left children called X minus and a right children called X plus. For instance, if you start with this one, minus 1/2, you have this is the left children and this is the right children. Okay, then you declare that the right children is bigger, the right children of X is bigger than X in the linear ordering, and also all the descendants of the right children are bigger than X. So on the other side, the left children of the left child of a node is smaller than the node, and also all its descendants are smaller. So this is what is written here. So X is between, so X minus is the left child of X, and star means any descendant of it, so any prolongation of the sequence. All these are smaller, and on the other side, X is smaller than its right children and all its descendants. So in the picture, it just looks like this. Okay, now this is a dense linear order, total order, because, for instance, between these two, which are 1/2 and 1, there is this 3/4, which just sits in between, right? Because 3/4 is bigger than 1/2 because it's the right child of 1/2, but is smaller than 1 because it's a descendant of the left child. So 1/2, you first go to everything here is on the left. So I guess you got the picture. So please feel free to ask questions. So you have this total order. It's a huge total order. It's a proper class because the surreals form a proper class. Of course, if you don't like proper classes, you could stop at this level, which is the first uncountable ordinal. You can start at the level below this. And essentially everything that I'm going to say can be done in this fragment below omega 1. Otherwise, you get a proper class. Okay, so you have two binary relations. Let me add one page here. So you have total order. Sorry, you have this tree-like ordering, tree-like. And then you have the total order. Total. Tree-like is called simplicity, and total is written with just less or equal. This tree-like is called simplicity. Right. Now, an important notion is the notion of convex set. A convex set is just a set which is convex in the linear ordering, something like this. This is a convex set. So C, a convex class, sorry. C is a subclass of the surreals. Is convex if whenever you have X less than Y less than Z. This is X, which is up there. With X and Z, if X and Z are in C, then also Y is in C. So it's like an interval, but doesn't need to have subs extremes, right? Everything which is in between is inside. So exercise, if X is convex, is necessarily, it's convex and is not, and it has more than one point. Convex implies proper class. Because there are a lot of objects inside this blue, because there are objects which project into it very up in the tree. No, you can go very, very up in the tree and you can still be inside the blue region. Convex, not singleton. Okay, and another important fact is that if C is convex, then C has a simplest element. Simplest element. So, for instance, if you take let me draw it in. Let me draw something similar to this. If you take something like this, probably the simplest element is going to be this. Is the simplest in this convex set. No, 0 is outside. And why? So let me just make the slide here, which says the same thing more formally. So this is the definition of convex. Every non-empty convex subclass has a simplest element. This simplest element is essentially the intersection. In which sense? Surreal numbers are functions because they are transfinite binary sequences, so they are functions from an ordinal to a binary set. You can take the intersection of the functions, in the sense, take the intersection of the domains, and to prove that every convex subclass has a simplest element, you just take the intersection. This is an exercise. You do this. But it's not very important. The important thing is to know that there exists a simplest element in each convex class. A hint for the proof is written here. X is less than y if X is less than this intersection. The intersection is essentially the meet. Let me make a picture. This is the tree. If this is X and this is Y, this one is going to be the intersection, is the meet. The meet in the tree-like order. And if you this is if you take two elements, if you take a class of elements, a convex class, to find the whole intersection is the simplest element. The simplest element in C. Okay, why is it important, this notion of convexity? Because...
Excuse me, I have
yes.
A question. You're dealing with proper classes, which are, so I'm not very used to this notion. So which kind of operation that you must be careful about when you deal with proper classes in comparison with usual sets?
Essentially power set. You cannot take the power set of a proper class. But if you don't really like proper classes, you really could stop at level omega 1, then you don't get a proper class. Then you only have ordinals, countable ordinals. And omega 1 is the least uncountable ordinals. And then many of the things that I'm going to say with minor modifications work perfectly well in this fragment of the surreal numbers. In particular, already in these fragments of the surreal numbers, you can define a lot of operations like plus, times, exponentiation, infinite sums, and you can embed the transseries inside it. So you could really, if you don't like proper class, stop at, consider only countable ordinals and binary sequences of countable length. Of course, then some of the things that I'm going to say only work for countable sets. But you don't really need to be over worried. There will never be really problems with dealing with this proper classes. You can just imagine them as a set, except that, of course, it's not true that if you stop at level omega 1, it will not be true that, okay, it will not be true that, for instance, look at ordinals. It will stop at omega 1. It will not be true that every set of ordinals as a soup. It will only be true that every countable set as a soup. And similarly for the surreals. So the soup operations must be restricted to countable things.
Thank you.
Now, suppose now that you have two sets of surreals, sets, not classes. And suppose that L is less than R. L less than R means that for every X in L and for every Y in R, X is less than Y, no? So you have to imagine it in this way. So you have, again, the tree. You have L, which could be this, and R will be this, no? Okay, if these are sets rather than classes, you will always be able, then there exists X between the two. So you will always able to find an X here. Of course, L and R cannot be allowed to be classes. Otherwise, you could take R just the complement of L, and there will be nothing strictly in between. But if they are sets, there will always be room to stick something in between. And why? And moreover, the class of X satisfying this property is convex, of course. So the things which are in between form a convex, the things here are form a convex class. So it has a simplest element. So it has a simplest element called L bar vertical bar R. So this is the simplest element. With this notation, we indicate the simplest element between L and R. Imagine L and R as a partial Dedekind cut. It's not a real Dedekind cut because the union is not the whole class of surreals. Of course, since they are sets, the union of the two is not the whole class of surreals. So there will always be something in between, and there is a simplest element in between, which is denoted in this way. Okay. Maybe I should add another. Yeah, let me make an example here. Okay. Of course, if you don't like proper classes and you would like to stop at level omega 1, this will not be true anymore, but it will be true instead of taking sets, you need to take countable sets. So if you arrive only at level omega 1, it will remain true, but only for countable sets. Okay, now let's make an example. Consider again the tree. What is it? Okay, plus, 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 minus, plus. Okay, so you do plus, 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 minus, plus. So you arrive here. This node is the binary sequence plus, 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 minus, plus. And this guy here is the simplest element. It's written here. Is the simplest element, which is bigger than, let me just copy this, plus, 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 minus, plus, plus. Okay. So plus, 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 minus, plus, plus. This is going to be plus, 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 minus, plus. Okay, let me explain this. Okay, where is plus is this guy here, plus. Plus, plus, minus is plus, plus, minus, this guy here. Plus, plus, minus. Plus, plus is this. Plus, plus. Okay. We are looking for an x which is bigger than plus and also bigger than plus, plus, minus, but smaller than plus, plus. So bigger than the red ones. But smaller than the blue. Okay, well, not very successful, but this is x. And we are looking for the simplest such x, simplest. The simplest one will be denoted by this notation that we illustrated before. And I'm claiming that the simplest is this guy, is the black one above. Okay. Is that true? Is this example?
Actually, I think we have our first typo on the slides.
Yeah, it's not that one.
No, there's a plus too many.
So it's one less plus here.
Yes, I think so, yeah.
Okay, so it's not this one. So let's compute. So it's probably, it should be smaller than the blue. So where is it? It should be smaller than the blue, but bigger than the red. So it's going to be I need to take this probably, this one. So in this, so it's a plus, plus, minus, plus, 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 minus, plus. Plus, plus, minus, plus. Why is it smaller than the blue? It's smaller than the blue because it's a descendant of the left child of the blue. but it's bigger than both red ones because it is a descendant of the right child of the red. So it works, and it's the simplest one. There are many others which are in between, but they are all above. All the descendants of this black one will also be in between, but they are more complicated, right? Okay. Now, with this notation, I'm going to use, I need to introduce the notion of left and right option. Okay.
Can I ask a question about this example?
Yes.
So the L set here with two elements, without
Yes.
the first plus, the result is the same, right?
Yes, yes, the result is the same. The
Okay.
reason I wanted to, I wanted both is because I wanted to include all the ancestors of my black one.
I see. I understand.
I wanted to include all the, actually I forgot to put 0, but 0 is just the empty sequence. So I wanted to include all the ancestors.
Yeah.
So some of the ancestors will be bigger and some of the ancestors will be smaller, right?
Mm-hmm.
And the bigger ones, so bigger ancestors of X are called right options of X. And usually they are called XR. XR is the typical right option. And the smaller ancestors of X are the left options. And they're called XL. So the red ones, so if this is X, this guy here, it's a left option. So XL may denote either that or that. So it's a generic name to denote either that or that. And this is XR. So it's something which is simpler. Simpler, namely ancestor. Ancestor means simpler. Some of the ancestors will be left options, some other will be right options. Okay, now I can finally define the addition of two surreal numbers.
Sorry, I didn't understand why plus is a left option.
Plus is a left option because, first of all, plus is an ancestor of my X, of this, right? Because it's closer to the root. So it's on the path to the root. Secondly, this plus is less than plus plus minus plus. Why is less? Because every descendant of the X is a descendant of the right child of plus. So it's bigger than plus. So because it's a descendant, so if you project it on the horizontal line, if you imagine projecting this to the horizontal line, plus is less than plus plus minus plus.
Okay, thank you.
Right? So it's plus plus minus. so from the first plus to reach X, you first go right, but then it means that it's bigger. So if you go right and then you do whatever you want, what you get is bigger than where you start. Instead, if you start from something and you first go left, you always go to the left, right? Okay, so this is crucially important to understand this picture. Once you understand this picture, you can define addition. You want to define addition of two surreal numbers. So you want to do X plus Y. X plus Y is defined as follows. So is the simplest element which is between two suitable sets. Okay, what are the sets? So I write it this way. It's XL plus Y, X plus YL, and here you put XR plus Y, X plus YR. Okay, here XL varies on the left options of X. So it's not a single element. So actually there are many elements here. There are all the elements of this form. And of course, XL, XR, YR are defined similarly. So what is the motivation? The motivation is the following, that since XL is less than X, you want an ordered field. In particular, you want an ordered group. This implies a posteriori that this plus this is less than this plus this. So you must put this object between the left options. The left options of X plus Y, this will be among its left options. By induction on simplicity, you can assume that this guy here and these objects are already defined, because XL is simpler than X, is closer to the root. So you reason by induction on simplicity. So you can assume that this has already been inductively defined, all the objects of this form, and also this. Then you can and similarly for this. So then you can prove inductively again that all these guys are less than all these guys. Everything here is less than everything here. So there must be something in between. And the simplest object in between, by definition, is X plus Y. Okay. Now it makes sense. Okay, so this is this definition here. The addition of serial numbers is defined by induction on simplicity by this formula. XL and YR vary among left and right options of X and Y. And the idea is that the additions should be strictly increasing in both arguments. So you are, and this is in some sense the simplest possible definition of a binary function, which is strictly increasing in both arguments. And then you can prove that this makes the surreals into an ordered abelian group, and with neutral element 0, which is just, you put empty set on both sides. So you have no constraints. So 0 is just the simplest element of all. It's just the simplest surreal numbers because you have no constraint on the right and on the left. And you can prove that the opposite minus x is defined inductively by exchanging left and right options. Let me make a picture, or let's go to the previous picture. Okay, now you can start making some computation. For instance, why I call these guys -1 and 1, probably because -1 plus 1 is a 0. And you need to prove it with the definitions. And also 1/2 plus 1/2 is probably 1. So I've put the labels in this tree to fit with this idea. Okay, now if you look at this picture more closely, so 1 plus 1 is 2, is up here. You will see that on the rightmost path, maybe I should make a copy of this, or maybe erase all this mess that I did here. So to start again. Okay, so maybe now you see it better. It's going to be a bit complicated to do the computations according to the definition that I just gave, but fortunately, eventually, you will not need to. I cannot do these computations myself. I mean, it takes a while, but this representation of the surreal numbers is a very low-level representation. It's like if you want to do programming languages, write a software in binary code. So this is essentially binary code. It's not useful. We need a higher level representation of surreal numbers, which will come in a while. Now, this is very, very basic. Let me just remark that on the rightmost branch, you have exactly a copy of the ordinal numbers. You see, 0, 1, 2, 3, and then at some point you have something which is called omega, which can be essentially identified. It's an isomorphic copy of the ordinal numbers that you have there. While on the leftmost, you have the opposite of the ordinal numbers, -1, -2, -3. The opposite according to the group operation that I just defined. Okay, probably Vincenzo in his talk after tomorrow will give more proofs and examples. For instance, he will manage to compute 1/2 plus 1/2 equal 1, maybe. We can try, but I'm not sure I will succeed. So 1/2 is plus minus, right? So let's try to prove it, but I don't guarantee anything. Maybe it's easier 1 plus -1. Let me try to do that, which is probably easier. Okay. So let me try. So 0 is empty set, is the simplest element of all. 1 is bigger than 0 and empty set. So it's the simplest element bigger than 0. 1 is the simplest element bigger than 0. So on the right, you have no constraint. -1 is here. -1 is smaller than 0. And you have no constraint on the left. So it's the simplest element smaller than 0. 1 plus -1. It's equal. So this is x plus y is going to be left option plus y, x plus right left option. Then you have to do the right options. Okay, what are the left options available for 1? The left options available for 1 is just 0. So if you take x equal 1, the left option is just 0. Plus y, so plus minus 1. And then you have x, which is 1, plus the left option of y, nothing. So this term disappears. There is no left option of y. And then here you have xr, right option of x, nothing. There is no right option of x in this representation. So this term disappears. And then here you have x, this other term here is x, which is 1, plus right option of y, which is 0. Okay, then an additional exercise shows that this is 0 plus minus 1 is just minus 1, 1 plus 0 is just 1, and the simplest element between 1 and minus 1 is indeed 0. This one is the simplest element between minus 1 and 1. Okay, so you can just make some computations, and it works and gives you the correct labels. Okay, now you would like to define, okay, now exercise. This is an abelian group and so on. And this is a sketch of the proof, but I will not go into that. Everything is done by induction on simplicity. Let's go to multiplication. Multiplication. Sorry. Okay. How do you define x times y? Okay, you start with some observation. Take, for instance, you would like an ordered field at the end. So let's consider something like x minus xl. Take a generic left option of x and take a generic right option of y. So x is somewhere. It's projected here. The left option is somewhere else. It should be projected here, xl. Y maybe it's here, and yr is here. Okay. X minus xl should obviously, if everything works well, should be negative. No, positive, sorry. And this y is negative because you are subtracting something bigger from something smaller. So the whole thing should be negative, right? Now, eventually, if things work well, this should be equal to xy minus xly plus minus xyr by distributivity plus XLYR. So that means that X, Y, you take, should be smaller. You take this to the other side than this guy. So you decide, you put this in the official definition, you put this on the right options of XY. Similarly, with all possible changes of signs here. So, and these guys are already defined by induction. You can assume that they are already defined because they involve simpler elements. So the official definition is then this. So X times Y is the simplest element which ensures that these distributivity laws work correctly. So the thing that I wrote before is just, let's see, where is it? XLY. Did I write it correctly? Maybe I did some, should be somewhere here. Maybe I did some mistake of it's either this or that. XLY. XYR. So why there is a signs are wrong. So I take this to the other side. This should be a plus. And this should be a minus. Okay, so it's going to be exactly this, this one. This one. So you see, it's one of, in the definition of X times Y, it's one of the things that should be on the right, should be bigger than X times Y. Then you do all possible combinations, 4 combinations, and you get these terms here. Again, XL is not a single element, it's a generic object which ranges over the left options of X. So this is the definition of multiplication. And now you can prove that 1/2 times 1/2 is 1/4 and so on. And 1 is the neutral element and everything works well in the picture.
Alessandro, may I ask a question?
Sure.
So for the addition, your rule was that you wanted the map, the addition to be increasing with respect to both arguments, right? And here for the product, you seem to have another way of thinking using what you call the heuristics.
Yes, there is a different heuristic. Of course, you cannot use the same heuristic as before, otherwise you will get the same function. So addition is the simplest function, which is increasing in both arguments.
Yeah.
Multiplication should be a function which has some properties with respect to the order, but should also distribute over addition. I'm imposing in the heuristic the distributivity over addition.
Right.
Right?
Yeah,
so
right.
It should
It's clear, okay.
Yeah.
Okay, thank you, Alessandro.
Okay, so I'm fine with continuing, but if you want a pause or ask questions, I can stop for, wait for your questions for 5 minutes. You tell me.
Well, I'm fine with continuing too, personally.
Okay.
I just had an unrelated question regarding set theory. So I don't know if anyone can answer. So in NBG set theory, do you know if you can take class-sized intersections of classes? Like if you want to define the smallest class containing certain classes, do you know if you can do this, or?
Should be doable, no?
Well, the problem is you can't have a collection of classes of which to take the intersection of.
Right.
So that's the technical problem in that case.
Yes. Before
You
taking
have
the intersection,
comprehension,
you
but
be able to
only...
form. Yeah.
You don't have to answer. I just wanted to see if someone like knew this. But,
Yeah. No, but Vincenzo, I think, gave the correct answer. I mean, you cannot, for the simple reason that there is no, you cannot even form the family of which you would like to take the intersection, because it will be, well, no, actually you could, if it's, let's say, a definable, I mean, could be a family of family indexed by a single family. No, I suppose you could. I mean, I'm not, I should think a moment, but I don't see particular reasons why you cannot, provided you can form the family of which.
So if you can form a family, but it's okay, I think. But if you only have a property and you want to take the intersection of classes satisfying this property, then you would have to quantify over classes.
Yes.
And the usual specification scheme for NBG set theory is you have to quantify over sets, and then you can take the class of.
Yes. Yeah, there are, yeah, in certain set. Yes, yeah, you are correct, because I guess in NBG you cannot define properties which involve quantification over classes. Then you probably need to go to a stronger set theory like Morse-Kelley, in which this sort of things are allowed, but then there are further problems later.
Yeah, I guess we're going a bit off topic, but I think that there's also a message in the chat about this. And no, actually, I mean, you can quantify over classes in MBG, but you need to. So in that case, if you have a property which is given by a formula, then yes, you can take the intersection of all.
Where do I see the
all
chat?
such classes?
Oh yeah, in the chat, yes, but I'm not sure you can actually do this. But maybe you can. I mean, I just don't know. I mean, it's not so intuitive to know what you can do with NBG set theory. So.
Yeah.
But thanks for.
No, fortunately, everything we need to do can be done. But I'm not really over worried about this. If you cannot do it in some set theory, you choose another set theory.
Hi, Alessandro.
Okay, there is, however, yes, please.
No, sorry, go ahead.
No, there is an important set theoretic question which I forgot to say, which of course is of course, something that I skipped the proof of the fact that if you have L less than R sets, then there is something in between. No, then the class, this class is non-empty. No. This is an exercise. This is maybe, it's not, I mean, it's easy, but not entirely trivial. I mean, the point is that in the tree of surreal numbers, since the elements of L cannot go arbitrarily high, no, because here you have all the ordinals. So there is a boundary here, and there is nothing above, and similarly on the right. So and then you will able to, I mean, if you go, since you have a lot of space above this level, you will able to find something in between. But it's not, I mean, it needs a proof. Maybe Vincenzo can do it. I mean, everything that I will not manage to do, Vincenzo will do. But I mean, it's an exercise. It's not difficult, but it needs to be proved. Okay, so now we have.
Sorry.
So there was another question, right?
Yeah,
Yes.
a small question. Do you know if there is a way to express addition and multiplication through this definition that you gave, the Gonchor, the sign sequence?
In terms of binary code, in terms of binary sequences. For addition, yes, there is. For multiplication, there is, but it's probably a bit complicated. I'm not able to tell you. It's complicated. Certainly, for exponentiation will be a challenge. I really have no idea whether there is a definition of exponentiation in terms of binary sequences. I mean, of course there is, but nobody has found one for what I know. I mean, it's complicated to do the operations using this binary representation. But anyway, you can get more or less a hint from this picture of the tree of the fact that there is a certain asymmetry on the leftmost branch and the rightmost branch, because roughly speaking, each bifurcation should be smaller. Now, for instance, here you have after 1/2, you have 1/4 and 3/4, whose difference is 1/2. But probably if you take the next bifurcation, the difference between the children will be not 1/2 but 1/4. But there is something strange happening, you know, at the extreme situations. You have 2, but then you jump to 3 instead. So here there are some irregularity at the borderline. But otherwise, roughly speaking, each time you go up, this distance between the siblings becomes half of what it was before. Of course, then you arrive to a limit level. Things become complicated. I'm not able to do myself these computations. If you tell me what is this, I mean, as I say, there is a better representation of surreal numbers for which it will be much simpler to do computations. Okay, we arrived to multiplication. Okay, and then it's not difficult to prove that you get an ordered ring. And later we will see that it's actually a field. So there is an inverse also. Moreover, it's real closed. So every polynomial with coefficients in the surreals, if it changes sign, it will have a root. And as people know, once you have an ordered field with this property, it will be elementary equivalent to the reals. So it will satisfy all the first order properties of the reals. So you can transfer results from the reals to the surreal numbers. It's a non-standard model of the reals, but unlike the models which are usually constructed using, I don't know, ultra powers or things like that, it's very concrete. You don't need the axiom of choice to define this non-standard model. It's all the operations can be very concretely defined, especially if you put a limit on the height of the tree. Okay, now we can embed the reals in the surreal numbers. Okay, first of all, the rationals are obviously embedded just simply because it's an ordered field. every ordered field contains a copy of the rationals. Okay, we have already seen some rational numbers. Those appearing at the finite levels of the tree are just the dyadic rationals, namely the denominator is a power of 2. So the rationals of this form correspond to finite levels of the tree, namely in binary, they are just finite binary sequences. The birthday is finite. So these are the dyadic rationals. Instead, rationals like 1/3, which is not binary, the birthday of this will be omega. So you need to go a bit in the tree. So for instance, you have 0, 1, 1/2, 1/2 appears. And then here you have, we said after 1/2, we have, what was it? 3/2, I forgot, maybe. Was it there? Yeah. But let's speak, okay. No, sorry, it's 3/4, 3/4. 1/2, 3/4, 1/4. So the dyadic ones will be at finite levels. Then 1/3 will be, you do some zigzag, and at some point at level omega, you will find 1/3. But at level omega, you will find also pi, square root of 2. You will, at level omega, you will find all the real numbers. Okay, let's be more precise. So, where are we? Okay, you have the rationals, no problem. Now, how to embed, in order to embed the real numbers, you do something very simple. You take all the dyadic rationals you identify a real number with the simplest element, which is between the dyadic rationals smaller than r and the dyadic rationals bigger than r. So the real number produces a cut in the dyadic rationals. If you want to identify your real number with a surreal number, you just take the simplest surreal, which determines the same cut on the dyadic rationals. The dyadic rationals are already identified with surreal numbers. And then you can immediately identify the reals using this notation. This notation is slightly different than the one we used before, because I'm not claiming, before we use the notation, this notation here, when we use this notation, it means that this object is not only smaller than x, but also simpler than x. Here we are not claiming that r minus is simpler than r. We are only claiming that it's maybe we could, I don't know, but we just put all the dyadic rationals, simpler or not, I don't care, all the dyadic rationals smaller than r in the linear order or bigger than r, and we take the simplest element in between. Okay. Okay, now you can prove, this is also an exercise if you want. I mean, the rule is that everything that I'm not able to do, it's an exercise. It's an exercise for you. You can prove that a surreal number is a real number in this representation, if and only if the birthday is less or equal to omega, first of all, either is finite, or length omega, but in case it has length omega, it's not eventually constant. Because at level omega, you will find lots of things which are not reals. Let's go again to the picture. Okay, so at length omega, you will find all these objects. Some of them are real, but some of them are not real. For instance, omega itself. Omega itself is not a real number, but it has birthday omega, or 1 over omega. This is infinitesimal, is not real. But all the real numbers will appear either at this level or below, at finite level. At finite level, and which ones are the real numbers? The ones which are not, the ones at level omega, the ones which are real numbers are exactly the ones which are not eventually constant. So they keep doing zigzag. So they are never eventually left, 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 or right, right, right. Because, for instance, if you take 1 and then you go all left, 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 always left, you get 1 over omega. You get something infinitesimal. While if you go always to the right, you go omega. If you go to 2 and then you go always to the left, you will probably get, I'm not sure, maybe 2 plus 1 over omega, 2 plus an infinitesimal in any case. No, sorry, 1 plus an infinitesimal. Like here, if you do 1, you get 0 plus an infinitesimal, 0. Okay, so in any case, those which are not eventually constant are the real numbers. In some sense, this is, according to Conway, the simplest definition of the real numbers, simpler than Dedekind cuts. So you could have stopped at level omega from the very beginning and define the real numbers in this way. Okay. Now, we already said that we can embed not only the real numbers, but also the ordinals, because just on the left, on the rightmost path, you have the ordinals. A copy of the ordinals. 0, 1, 2, 0, 1, 2, 3, and so on. So the ordinals are on the leftmost part. If you want to represent the ordinals using this notation here, you get that the ordinals are those which have no constraint